change of plans. Mohammad unfortunately cannot present as he's a bit unwell, but nothing too serious. But fortunately, we have Shengwu Li, who very kindly accepted to step in. He's going to present the paper, Investment Incentives in Near Optimal Mechanisms, with Mohammad Akbarpour, Stock Duke Kominers, and Paul Milgrom. And guest panelists are Nicole, Immorlica, and Yannai Gonczarowski. Sorry for mispronouncing your names. The format of these seminars are as follows. So we have a 60-minute presentation with time for interim questions from the panelists, followed by a 15-minute Q&A session. We request all attendees to keep their microphones muted during the talk. However, please, okay, so usually we have a session with, so we have the chat section, but we don't have any co-authors. So it's better if we just keep it open. So if you have some questions, we can interrupt Shengwu live. And, but also, you know, for the more, let's say, longer questions, we can wait for the Q&A session at the end. So the talk is recorded. Before I hand over to Shengwu, let me invite you to our seminar for next week. Caroline Thomas from UT Austin is going to present Social Choice Undergraduate Learning with Yiman San and Takuro Yamashita. Guest panelists are Margaret Meyer and Yusuf Alimaki. As usual, you can find more information on our website or by following us on Twitter. Thank you, Shengwu. The mic is yours. Or I should say, Shengwu Mohammad Li.
Thanks so much. This is, it's lovely to be here. I'm in Mohammad's guest room. Mohammad is comatose in his bedroom, two rooms down. He is not in a state to give a presentation. And he told me this about 45 minutes ago, but fortunately I know the slides. So this is, you know, this will be fun.
Give him our well wishes from everyone for a speedy recovery.
Yep. I think, you know, between getting tenure and getting sick, he's probably, you know, up ahead in the bargain. So this is, oh, thank you. Cheers. I have cappuccino. This is the best. So this is a paper with Mohammad, Scott, and Paul about, you know, what happens when we take some kind of approximation algorithm, when we build that into a mechanism, and then we ask, is the approximation still a good approximation when we expand the game a little bit, when the players, instead of coming into the game with fixed values for winning an object, instead are able to make investments that could change their value. Now, this is not reflected in the slides yet, but this recently became a 5-author paper because one of Paul's students, Kevin Lee, found a way together with Paul to very substantially generalize the main result. And so I'll get to that when it comes up. All right, so this is you know, about a basic question in mechanism design, right? You know, we want to allocate resources, we want to set prices for those resources. How should we do that? Who should get what? How much should they pay? And the usual answer, a beautiful answer, is to say we should use a Vickrey-Clark-Groves mechanism. This has several advantages. It's strategy proof, right? It's a dominant strategy for all participants to reveal their values for the resources. It just definitionally selects the efficient allocation. So it's completely efficient when it comes to deciding who should get what. And it turns out that it's got an equally fundamental but less well appreciated property, which it yields efficient investment incentives. And what do I mean by that? Well, I mean that suppose we've got some profile of values and we're running a VCG mechanism, and I change just one of the bidder's values, holding everybody else fixed. Well, under a VCG mechanism, the change in that bidder's value is exactly equal to the change in social welfare. Sorry, the change in that bidder's payoff is exactly equal to the change in social welfare. So if I change the bidder's value by 100 and social welfare rises by 80 in a VCG mechanism, that means that bidder's payoff is changing, is rising by 80. And so in some sense, this prices all the externalities, right? You know, any change in your private value that is good for society, that is good for welfare, is also going to be reflected in your private payoffs. And so what that means is that if the bidder could invest, he could pay a cost to change his value, he would gain by investing if and only if net social welfare increases. Now, this is not an original observation of ours. This goes back at least as far as Rogerson 1992. And there's a great paper by Dirk Bergman and Yusuf Valimaki that thinks a bit about this under, if you were gathering information ahead of the mechanism. Now, there are some important caveats to this analysis of VCG mechanisms. One caveat is that to make a good investment, the bidder has to know the price he faces, right? If he's unsure about the price, then it might be that he makes an investment thinking he's going to get the object, but somebody else wants the object a lot more, so he doesn't get it, in which case it was a bad investment ex post. Though it might still be a good investment ex ante, and we can get to that. Another caveat is that if you have multiple investors, then you can get coordination issues. There can be, if multiple bidders in a VCG mechanism simultaneously make investment decisions, there can be good equilibria and there can be bad equilibria. And you can have equilibria where everybody makes a bad investment, but it would, the problem is that their investments are complements with each other in the game. And it's only worth making this investment if everybody else is doing it too. Now, the caveat that we want to focus on today, is that VCG mechanisms rely quite sensitively on exact optimization. They assume that if you know the bidder's values and you know the constraints, that you can produce the exactly optimal allocation. And moreover, you can compute, were we to remove one of the bidders one at a time, what the exactly optimal allocation would be when we delete just one of the bidders from the set, right? That's what you need to do to compute the victory prices. Now, that's a problem because lots of real-world allocation problems are computationally hard. So you might think about spectrum auctions with local interference constraints. This graph up here are the pairwise interference constraints for the 2017 Federal Communications Commission incentive auction. And so what happens in this auction is you need to figure out which TV stations should remain broadcasting on the air. Each node is a TV station. Each edge is an interference constraint. So you want to find the highest value set of TV stations to remain on the air, subject to the constraint that no two adjacent stations should share the same channel. So you've got some number of channels. You need to color the nodes, the TV stations. You need to assign stations to channels, nodes to colors, so that no two adjacent stations, nodes, share the same channel color. And of course, this is one of the canonical NP-complete problems in computer science, figuring out whether you can even do this, which are feasible allocations, can be tough. Similarly, in combinatorial auctions, under mild conditions, it's hard to compute what the optimal allocation of bundles to bidders is. And there are various integer packing problems, and I'll get to one shortly, in which it's similarly hard to compute the optimum. Now, in practice, when we have these kinds of hard constraints, we don't give up on running mechanisms. What we do is we use approximate allocation rules in order to figure out what the mechanism should do. So we say, okay, it's just too complex to compute VCG, we're going to do something else. And that something else hopefully is always within some fraction of the optimum. Maybe we can prove some bound that says it gets at least half or a third or 90% of the optimum. And our research question is essentially this. Suppose we take an approximate allocation rule and we use that rule in a strategy proof mechanism. What happens to the incentives to invest efficiently in the relevant resources? So if this was a VCG mechanism, the investment incentives for an individual bidder would be perfect. You would make investments if and only if they were good for society. Is that still true when we use an approximation algorithm?
So may I ask a quick question, Shengwu? So, I mean, spectrum auctions specifically there, even if you do approximate packing, those are still, ascending/descending auctions, so they're still exactly incentive compatible. But if you run Vickrey-Clark Groves in general with an approximate packing rule, is incentive compatibility even maintained?
So Yannai is absolutely right. There's one way you might use an approximation algorithm is you might say, I'm going to try to compute approximate victory prices using my algorithm. And that can destroy strategy proofness. It can be that if you compute prices this way, even if your algorithm is very good, the prices can be very wrong. This was a feature of the incentive auction with these constraints you see. It turned out that even if, the FCC said at the time, we have an approximation algorithm that is within 99% of the optimum most of the time, why don't we use this to compute the approximate victory prices? It turns out that the corresponding victory prices were so far off that some bidders faced negative prices. That's to say, they were meant to be paid to leave the air, and instead of being paid for their TV station, they would both lose their TV station and have to pay the FCC. And that, it turns out, is not close enough to the optimum for you to use that. So we are not doing that. That is one way you might use an approximation algorithm to say, I'm going to pretend that the approximation is completely efficient and use it to compute not only allocations, but prices. That will often damage strategy proofness. What we are going to do instead is we're going to take an algorithm where we're going to say, we know this algorithm is inefficient. It's only approximately accurate. We're going to take its allocations as given, but then we are going to compute the correct threshold prices that correspond to that algorithm. And so we're going to need to look at monotone algorithms because those are the ones for which the relevant strategy-proof threshold prices will be defined.
Can I ask another question here? Just here indicating my lack of knowledge is approximation literature. I mean, maybe this is not that relevant for the real world, but is there a similar question could be asked without the investment question? So in other words, the types are already there. How close can, I mean, maybe this is Yannai's question in a way.
So this is a great question.
Or
So that is a great question, and the answer is mostly due to Nicole and Yannai and their friends. The EconCS community has thought a lot about both. If I have an algorithm that's only approximately right, to what extent can I use this to compute prices, and when is that a good idea? And not only that, they've also thought about the question, if I have an algorithm that's approximately right, but it's not monotone. That's to say, if, so to make an algorithm into a mechanism, it needs to satisfy a certain monotonicity property. If you have a good algorithm, but it doesn't have that, so you can't make it an exactly strategy-proof mechanism, is there some way to correct the mechanism, correct the algorithm so that it becomes monotone without making the approximation worse? And so that's a beautiful paper by Jason Hartline and Brendan Lucier in the AER from some years back. So those are important questions. I think they've substantially got good answers. Okay, so I want to give you an example so that it's concrete what we're talking about. And so I want to talk about the knapsack problem, which is a canonical hard problem in computer science. The way it works is that we've got a bunch of bidders, each of whom has a value and a size. Think of this like they have a value for being packed. And I have a knapsack, which has a capacity. So the thought is like, imagine I'm shipping integer cargo on a ship. So I can't split your cargo up into little pieces that will make you unhappy. But you've got some value for your cargo being on the ship. And we want to figure out whose cargo should get on the ship. Now, the challenge, right, is we want to figure out the value maximizing set of bidders to pack, subject to the sum of their sizes not exceeding the capacity constraint, right? Not exceeding the knapsack's capacity. This is a canonical hard problem. If P is not NP, then there's no fast algorithm that solves it exactly. Now, this is a solution for the problem, which is called the greedy algorithm. This is Danzig's greedy algorithm. What we do is we sort the bidders by their value divided by their size in descending order. So the little bidders have a value over size of 1, and the big bidder has a value over size of 1/2. So the big bidder, he goes to the back of the line. And what we do next is we pack bidders from left to right, just greedily, with the bidders who have the highest value per unit size and the next bidder. Eventually, we run out of room in the knapsack. We're going to stop when the next bidder doesn't fit. And that's the output. Now, it turns out that this algorithm can be used even when the values are private information. So let's suppose that the bidder's sizes are observable. We know how big their cargo is, but we don't know what their value for being on the ship is. Well, we can use a strategy proof mechanism. What we do is we ask the bidders to report their values. We take those reports as gospel truth. We run the greedy algorithm on the reported values, and we charge each bidder their threshold price, which is to say, for each bidder, we ask, what is the least value they could have reported such that the algorithm would still pack them? So for the first two bidders, the little bidders, in order to be packed, they need to come ahead of the big bidder. So they need a value over size of at least 1/2, which means that they need to report a value of at least 5, which means that their threshold price is 5. For the big bidder to be packed by the greedy algorithm, it needs to be that he comes ahead of everybody. So he needs a value over size of at least 1, which means that he needs a value of 12. So his threshold price is 12. So the little bidders who are packed, they each pay 5. The big bidder faces a threshold price of 12 and is happy not to be packed. Cool. Now it turns out what I want to show you is that even though we have an allocation algorithm and a strategy proof mechanism, and that mechanism here, it's in fact managing to compute the exact optimum, right? The best packing is to do just the 2 little bidders for a total welfare of 20. When I add investment opportunities, that can screw the algorithm up. It can severely reduce welfare. And so here's an example. Let's imagine that the big bidder who's not packed, he's got utility 0. But what if he could invest ahead of time to raise his value to 14 at a cost of 1? So if he was to raise his value to 14 and then report truthfully 14 to the mechanism, he would get packed, right? His threshold price is 12, so he'd have a value of 14 minus a payment of 12 minus the cost of 1, but that's positive. So it's worthwhile for him to make this investment. On the other hand, this investment is not only this investment is pretty bad for welfare. If he doesn't make this investment, we pack the little guys and we get a welfare of 20. And if he makes this investment, we pack the big guy. He's got a value of 14, but he's paid a cost of 1, so welfare is 13. So I've substantially damaged the algorithm's outputted welfare by adding an investment opportunity. So what's going on? Like, why is this happening? It turns out that in an exactly optimal algorithm. Now, if I've got an exactly optimal algorithm and I compute the threshold prices, those threshold prices are the VCG prices, right? So the VCG prices do the job of eliminating all the externalities. They make it so that when you change a bidder's value, the change in their payoff is equal to the change in social welfare. Now, in the paper, what we do, is we show that exact optimization is essentially necessary for this property. If you have a strategy proof mechanism and it's not an exact optimization, or in some sense, it's got to exactly optimize at least on some constraint set. But it can't, a lot of natural approximation algorithms don't have the form of optimization that is needed for this nice property that you price all the externalities. And because of that, they will typically not get the investment incentives exactly right. Now, with other kinds of allocation algorithms, in principle, you could think that there are 2 externalities that arise. One externality is that the bidder's threshold price is not equal to the social cost from packing him, right? So what do I mean by that? Well, in this case, the big bidder had a threshold price of 12, but when we pack him, we lose 20, right? The way the algorithm changes when we pack him is it knocks out 2 bidders whose combined value was 20. And so the big bidder is investing thinking that the price he privately faces is 12, but the price he should face, the price that society should charge him is 20. And so that's an externality of 8, right? So one externality could be that if I'm using an approximation algorithm and computing threshold prices, the threshold prices are wrong. So that's a kind of a threshold externality. The prices you face don't reflect the cost to society of packing you. But another thing that can occur in an approximation algorithm is you can get a bossy externality. And what do I mean by that? I mean that sometimes in an approximation algorithm, you can change your value without changing whether or not you are packed, but you might change who else we pack, right? It might be that you raise your value and the algorithm locates a different approximation, and it still doesn't want to pack you, but it's figured out something else better it should do. Now, of course, if we're running a threshold price mechanism, we're using a strategy proof mechanism, then those changes are not priced. So those changes are also externalities, right? They're also unpriced effects on the other bidder's welfare. Now, it turns out that when you're using approximation algorithms, you can encounter both of these externalities. You can encounter both threshold externalities and bossy externalities. It turns out that only some of these externalities are bad for performance under investment. And we will show you exactly which those are. And so if you can check, only the relevant externalities need to be excluded from the algorithm in order to have investment work well. Now, this is the basic model. It's not very unusual at all. It's probably familiar to many of you. But just to create common knowledge, our model involves, as a primitive, what we call an allocation instance, which specifies for some set of bidders n, a value profile. Think of this as a value for being packed in the knapsack, and a set of feasible allocations, which is a subset of the power set of bidders. So this can include constraints like the sum of their sizes can't exceed the knapsack's capacity. It can include constraints like you have 3 TV channels, and whichever bidders you choose to have be on the air, they can't, if they're adjacent, they can't share a channel, right? All of those constraints, we're just going to collapse into this arbitrary set A. Now, an allocation problem consists of a collection of instances. So an example of an allocation problem is the knapsack problem. The knapsack problem consists of all the instances I can specify with value profiles and feasibility constraints that involve sizes and capacities. Now we're going to assume that for every set of feasible allocations, the corresponding value profiles we might encounter is a product of closed intervals. The reason we're doing this is because Paul is on the paper and we like the envelope theorem. And when we have nice closed intervals, we can do the envelope theorem. Now, a natural question is this only about individual, one-dimensional types? This is only about things like, you're either packed or not packed. It turns out that that's not essential to the argument. In the paper, we generalize this to multi-dimensional types and some kinds of combinatorial auctions. But for today, let's think about it's one-dimensional. You're a TV station. You have a value for remaining on the air. We're going to decide whether or not you remain on the air. Now, an allocation rule, which we're going to call an algorithm, is going to choose a feasible allocation for each instance. So this allocation algorithm X is a function of the value profile and the feasible allocations, and it's going to just output, an allocation. So we'll think of Xn as an indicator variable for whether or not bidder n is packed at a given instance. A payment rule just specifies a payment for each bidder, and a mechanism consists of an algorithm and a payment rule. Cool? Now, this is the usual definition of strategy proofness. We want, it to be incentive compatible to correctly reveal your value. And this says that a mechanism is strategy proof if at every instance, for every bidder, revealing their true value is the best response, no matter what values the other bidders have. Right, so we're using the usual quasi-linear utility, right? You have a value for being packed. Xn is an indicator for whether you're packed. Pn is your payment. An algorithm is monotone if for any bidder n, and for any instance, there exists a packing threshold Tn that depends on the other bidder's values and on the feasible allocations, but crucially, not on his own value, such that if the bidder's value is above the threshold, then she's packed. And if it's below the threshold, then she's not packed. Now, it's clear that if I have a monotone algorithm, there is a strategy, there is a pricing rule I can use to make the algorithm strategy proof. Namely, I should charge the threshold price, right? Because if I charge the threshold price, the argument is just like a second price auction, right? If your value is above the threshold, you want to pay your threshold price. If it's below, you don't. So you should truthfully reveal your value. You can't change your threshold price because it doesn't depend on your own report. Now there's a proposition from Lemon et al. In 2006 that says this is an if and only if relationship. So not only is it true that every monotone algorithm can be made strategy proof, there exists a payment rule that makes an algorithm strategy proof if and only if that algorithm is monotone. So we're going to restrict attention to monotone algorithms, although there's an important literature in Econ CS that thinks about how you can take non-monotone algorithms and convert them to monotone ones without making them perform much worse. Now, it turns out that the strategy proof payment rule is essentially unique. So if an algorithm is strategy proof, then there exists some functions Fn that don't depend on the bidder's value. They depend only on everybody else's value and the feasible allocations, such that that bidder's payment is equal to an indicator for whether they are packed, multiplied by their threshold price, plus this function that is strategically irrelevant. And so what that means is that if you were considering an investment in a strategy proof mechanism, it doesn't matter which strategy proof mechanism it is, provided they have the same allocation algorithm. Because your net return from an investment, right, the Fn term is going to drop out. If I have two strategy proof mechanisms that use the same monotone allocation algorithm, your return from investment will be the same in both. And so the investments you'll make will be the same in both. And what that means is that if you give me any strategy proof mechanism, the algorithm alone is sufficient to determine the investment incentives under the mechanism, right? I can inspect directly what the algorithm is and tell you which investments that bidder would like to make and when. Now, of course, when exact optimization is not feasible, we approximate. And there's a truly vast computer science literature that studies fast algorithms for computationally hard problems. Now, this is part of complexity theory. In order to play nice with the rest of complexity theory, this literature uses worst case guarantees, right? It says where we want a polynomial time algorithm that always gets within some fraction, p of the optimal allocation. And so we're going to use those worst case guarantees today, because that will mean that our results will speak to their results, right? When we have an algorithm that is approximately good in the sense meant by a computer scientist, we want to be able to say, is it approximately good when we make it into a mechanism and when we worry about investment? And so I'm going to use this function W to denote the welfare achieved by the algorithm X at some instance VA. So that's just the sum of the values of the packed bidders. I'm going to say that for some parameter beta, the algorithm is a beta approximation. If for every instance of the problem, the welfare that the algorithm produces is at least beta times the welfare of the efficient allocation. So even though the efficient allocation is hard to compute, we're going to compare it to that. That's our benchmark. Now, what's an example of an approximation algorithm? We've already shown you the greedy algorithm. Now, the greedy algorithm, in the worst case, gets a share of 0 of the optimum. So the greedy algorithm is at best a 0 approximation for the knapsack problem. But it turns out you can get a meaningful approximation by making it just a little bit smarter. So the smart greedy algorithm works like this. We are going to run the greedy algorithm and look at that output. We're going to see how much value the greedy algorithm delivers. And we're going to compare this to what would happen if we chose the single bidder who has the highest value. So we're either going to pack the greedy output or pack just one bidder, whoever has the highest value for being in the knapsack. And I'm going to just output whichever of these is better. Now, this is a simple modification, but it turns out to be a powerful modification. The smart greedy algorithm is a half approximation for the knapsack problem. So that's to say, no matter what the bidder sizes are, no matter what their values are, no matter what the knapsack capacity is, the smart greedy algorithm delivers at least half of the optimal packing. So now we're going to ask what happens when we've got a nice approximation algorithm, a beta approximation for some non-trivial data.
Sorry, and
Yes.
just to clarify, it's still monotone.
Yes, it's still monotone. The smart greedy algorithm is still a monotone algorithm. You know, the argument for that is not long, but I'm going to skip it in interest of time.
No, I agree. I just want to make sure.
Yeah. To create common knowledge, thanks, Yannai. The smart greedy algorithm is also a monotone algorithm. It too has corresponding threshold prices that mean we could use it in a mechanism. So here's the question, right? We've started with a monotone algorithm. Suppose we run the corresponding strategy proof mechanism. We know that if we have efficient allocations and it's strategy proof, well, then it's a VCG mechanism. And so it has efficient investments. Is it true that if we have near efficient allocations and it's strategy proof, we have near efficient investments? And so to make this claim precise, I'm going to define what it means to have near efficient investments. So the thought here is that suppose that some bidder chooses between having some value V upper bar at some cost C upper bar, or some value V lower bar at some cost normalized to 0. So we're going to think of this as an investment technology. So the bidder can make an investment and will decide whether or not to make that investment. And so given some investment technology and his threshold price, we are going to let the bidder choose an investment to maximize his payoff under the corresponding strategy proof mechanism. So B star, this object just denotes the best responses to the mechanism, right? He can either make the investment or not. B star is just the set of best responses given that he's going to report truthfully. It's optimal to report truthfully whichever investment you make, given the mechanism he faces. And he's of course considering the value he gets, the price he pays, and the investment cost that he might pay. Now, we're going to measure welfare, including investments, W bar, that just says, let's look at what happens when the bidder best responds, and we're going to count the cost of investment as a cost, right? We're going to count that along with the rest of welfare. Now, there's something unnatural about this formulation, right? Because we are assuming here that the bidder is making his investment knowing what his threshold price is. And that's a bit weird because the whole point of a mechanism is the bidders have a lot of private information. They might make decisions not knowing what the other bidders' values are. We might have to, we the designers certainly don't know what the other bidders' values are, or we wouldn't be running a mechanism in the first place. Why are we letting the bidder know his threshold price at the point he's making the investment? It turns out that all our results extend appropriately when you have incomplete information. That's to say, imagine that instead of the bidder making an investment with full information about the other bidder's values, there's some probability distribution over the other bidder's values, and the bidder is making whatever investment is in expectation best for him. Our results will generalize to that case. Part of Kevin's contribution to this project and why he's now a co-author is showing us why that's true. But for now, let's imagine, just so to get at the core logic of the result, let's imagine you know the threshold price, even though that's not important, it turns out, for the argument.
Shengwu, do you also, you have this binary, like either I invest or I don't, and I don't really see why that's very essential here. Like I could have just, some function that maps the investment to a cost and
yes,
right?
Yes, totally. So you would need to worry if it wasn't binary, if it was some, if you had uncountably many investments or something, we would worry about the existence of maxima. We need to write, ints instead of, but subject to those constraints, right? Like certainly all of our arguments are without loss of generality if you instead wanted to compare to, say, finitely many investment opportunities. So binary is mostly without loss. Now, what's our benchmark? We're going to take a fairly demanding benchmark. We're going to think about what the social planner would do if she simultaneously controlled the allocation and the investments. So our benchmark is you're going to choose the best investment, given that you're going to optimize the allocation after that investment has happened, optimizing it exactly. Now, if you wanted to generalize this to incomplete information, the comparison is what happens if the bidder makes a best response investment given his beliefs about the other bidder's values, comparing to a social planner who makes the investment that is optimal in expectation, given that she doesn't yet know what the values are, and then we reveal the values, and then she gets to choose the allocation, right? That's the comparison that would be the correct generalization of these results to the case of incomplete information. I'm going to say that an algorithm is a beta approximation with investment if for any investment instance. So an investment instance involves an investment technology for one bidder, values for the other bidders, and some set of feasible allocations A. If the welfare the algorithm delivers, including investment costs, is at least beta times the first best that you could get, including investment costs. So notice, this standard is not requiring that all the investments are efficient. We're only requiring that welfare net of investment costs should retain that same fraction of the first best. It should be a beta approximation for some beta. Okay.
You subtract the investment costs. Like, don't you get the same results if you just like don't count the investment cost if it's like a transfer? Because it's subtracted on both sides, isn't it?
So it's subtracted on both sides, but we're multiplying that subtraction by beta, right? It's beta times welfare net of investment costs. So I think our formalism will distinguish between investments and transfers, though I need to think more carefully about that.
Okay.
Can I ask another question? Because I'm a bit confused about the welfare benchmark. So let's stick with a case where the values are known to, are common knowledge amongst the agents, okay? So what you're doing here is you're maximizing, so somebody's maximizing their investment given that they know everybody else's and so on. Now the benchmark, correct me if I'm wrong, because I might have missed it, is that suppose that the mechanism designer, the welfare maximizing entity knows the values and so doesn't know the values before the investment decisions are made, but knows the values once the investment decisions are made. Right?
So, okay, so the thing I've written on the slides is full information, right? You know the values at the start, but the generalization, you're right, would be you don't yet know the values. You know, the investment has to happen many months before the mechanism is run. Nobody knows the values. We're going to learn, the passage of time will bring us information, but we have to start the investment now if it's going to happen. Right? So we're going to choose whether to start the investment. Then we're going to learn what everybody else's values were. Then we're going to choose an allocation.
But so here's my difficulty is I can buy that in some environments, the agents know each other's valuations. I find it more difficult to imagine, even as a benchmark, a case where the welfare maximizer. I mean, yeah. So maybe I'm missing something. Maybe you're looking at it exposed or something like that.
Yeah. So the way I've written this, it's a very demanding benchmark, right? This is an omniscient social planner, right? I'm not proposing this as a serious procedure we should undertake. I'm proposing this as a thing we can compare things to.
Right.
I think that the idea is that if Shengwu can prove with respect to this benchmark that his theorem holds, then if you think this benchmark is too strong, then for sure Shengwu's theorem holds even with weaker benchmarks.
Sure.
Yeah.
So,
I like
is the result going to be of there is a beta greater than 0 such that, or are you going to give it a number? Because if it's
going to be a number, it's going to be the same.
Okay.
Number.
Okay. Then it's interesting. Okay. So then I fully take the point. Okay.
Cool. So I've got these investments. What happens? I've got an algorithm with some beta guarantee. I'm going to add investments. How do the investments affect the guarantee? So an easy observation is that for any beta, if the algorithm is not a beta approximation, it's not a beta approximation with investment. Why is that? Because you can have a trivial null investment technology, right? Where there's no real change you can make to your value. So a necessary condition for being a beta approximation with investment is that you should be a beta approximation before we consider investment. So you can't improve the guarantee by adding investment possibilities, but you can make it a lot worse, it turns out. So here's a theorem. For all beta strictly less than 1, there exists a beta approximation for the knapsack problem that is no more than a 0 approximation with investment. So what this says is there is no nice continuity here. You can be as close to optimal as you like with your algorithm, and closeness to optimality by itself is not sufficient to make any guarantees about what happens with investment.
So here I have to echo Francesco's question again, because maybe this is an artifact of the very strong benchmark, and maybe a slightly weaker benchmark would not give this impossibility, right?
Let me show you the counter example, which I think you'll see does not require a very strong benchmark.
Fair enough.
It doesn't even require any uncertainty of any kind about the other bidder's value. So this is a satisficing algorithm. What happens is that if bidder 1's value is at least 99% of the total value, pack her only. Otherwise, optimize exactly. So this algorithm is not always going to be fast. It will sometimes be fast. What happens is if bidder 1 is pretty good, we pack her and we call it a day. And otherwise, we're going to take our time to figure out what the optimum is. So suppose we have 2 bidders. And so wait, first, this algorithm is clearly a 0.99 approximation. It's 0.99 by construction, right? Because the only time I'm not optimizing exactly is when bidder 1 is at least 0.99 of the total. Suppose we have 2 bidders and they both fit in the knapsack. If bidder 1's value is at least 0.99 of the total, we'll pack her only. And if not, we'll pack both of them because they both fit. So bidder 1 is always being packed. So her threshold price is 0, right? She doesn't need to pay anything to be in the knapsack. Suppose she can either have value 0 at cost 0 or a value of k plus epsilon plus some cost at some cost k. Now, if she doesn't invest, her payoff is 0. If she does invest, her payoff is epsilon, right? Because she's got a value k plus epsilon minus a price of 0 minus a cost of k. If I have a large enough k, then bidder 1's value is at least 0.99 of the total. So only bidder 1 gets packed. What's the welfare? Well, the welfare is a value of k plus epsilon minus an investment cost of k. You get epsilon. What's the first best welfare? The first best welfare is V2 plus epsilon, right? Because I could both get the epsilon of value from bidder 1 and also pack bidder 2, but I'm screwing this up, right? I'm forgetting to pack bidder 2. And so what's the approximation ratio? The approximation ratio can't exceed epsilon over V2 plus epsilon. Epsilon can be chosen arbitrarily small, so the ratio is 0.
So just to make sure that I follow your definitions from earlier, this is an example for what you call the bossy externality?
Yes, this is an example of a bossy externality, exactly. Bidder 1 is raising her value. She is causing bidder 2 not to be packed. She is knocking bidder 2 out of the packing, even though she is not changing her own allocation.
Okay, thanks. And even though it doesn't look monotone, it's actually monotone in the sense that you need it to be monotone for this is raising bidder 1's value can cause bidder 2 not to be packed. But not
that's
bidder
consistent
1.
with our definition of monotonicity. Monotonicity just says raising your value should never cause you not to be packed.
Yeah.
And that is true here. Okay, so what that shows exactly, as Yannai observes, is this algorithm has a bossy negative externality. Now, this is not just a feature of this algorithm that I've magicked up to be unreasonable. There is a canonical, what's called a fully polynomial time approximation scheme for the knapsack problem that is shown in sort of every approximation algorithms textbook that is thought to be a pretty good way to pack knapsacks. It turns out it has exactly the same vulnerability. It too can be a 0.99 approximation for the knapsack problem, or 0.999 gets as good as you like. And it too is a 0 approximation with investment. So the question sort of is, when does all hell not break loose? when is a guarantee actually robust to investment? And it turns out that what we need is exactly this property. In words, if I take the algorithm, I've got some value profile, I'm computing I've got some allocation the algorithm outputs at that value, at those values. It's got to be that if we raise the value of a packed bidder or lower the value of an unpacked bidder, the total welfare of the other bidders does not fall. So, right, the problem we had just now is that when we raised the value of bidder 1, we stopped packing bidder 2. And so bidder 2's welfare fell. That's a bossy negative externality. Our condition is excluding these bossy negative externalities. We call it exponent to have something that rolls off the tongue a bit better. This says, give me any allocation instance and any change in bidder n's value. If n is packed and I raise her value, or if n is not packed and I lower her value, then the sum of everybody else's welfare must not fall. And the theorem says that this is what you need for the guarantees to pass through. So this is getting to that earlier comment. This is about being the same beta for any beta. If the algorithm is exponent and a beta approximation, then it is a beta approximation with investment. So it is the same guarantee. If you have, for example, the smart greedy algorithm is exponent. It's monotone. So we have a nice mechanism. It's an exponent algorithm. It's a half approximation. If I add any investment opportunity, the smart greedy algorithm still will remain a half approximation with that investment opportunity there. So examples of these, any exactly optimal algorithm is exponent. The greedy algorithm is exponent. The max of any set of exponent algorithms is exponent. So the nice thing about this property is it composes very nicely. You know, a common technique in computer science is to say, I've got some algorithms that are good for these kinds of cases. I've got other algorithms that are good for dealing with these kinds of cases. And when I compose them, when I say I'm going to use whichever is better, it turns out that that property preserves exponent. Smart greedy is yeah?
Can I ask something? Is there any sort of way of showing the converse? So something like if you have an X that is a beta approximation for all betas, it is X-bone or something like that.
So there's a weakening of X-bone for which the converse holds, and I might be able to get to it on the slides. But it, you know, if I don't get to it, there's a X-bone is sufficient for this nice property. It's not completely necessary. You can slightly weaken it, but the weakening is much less tractable and therefore much less useful. So smart greedy is exponent. Why is it exponent? Well, it's a max of the following set of algorithms. It takes the max of the algorithm that is greedy, the algorithm that packs bidder 1 for sure, the algorithm that packs bidder 2 for sure, and so on. Now, generally in mechanism design, we've got these classes of non-bossy algorithms, right? Where if we change a bidder's value without changing whether he is packed, then the allocation does not change. It turns out that any non-bossy monotone algorithm is also exponent. So for instance, the greedy rejection algorithms that were used in the 2017 Spectrum auction are non-bossy algorithms and hence are exponent algorithms. So there are some real algorithms that have this property. What's the intuition for the theorem? If you have
is there a p-test for knapsack that's exponent, or like is there a lower bound that you can't get efficient investments arbitrarily?
We don't know. We know that the canonical p-test breaks. We don't know if there is a fix for the canonical p-test, and that is a cool open question, but maybe one that requires real computer science of the kind that I am not good at.
But you have a converse to this theorem, so you could.
We have a converse to this theorem.
Maybe try to prove that there's a fundamental like contradiction.
There's a fundamental contradiction between the weaker version of weak exponent, which is what's needed for the converse, and the property of getting close to the optimum on knapsacks. So the intuition here for why this theorem is true is that if you have an approximation algorithm, the threshold prices in the mechanism may not reflect the social cost of packing the bidder, sure. But let's decompose an investment into two parts. So imagine the bidder wasn't going to be packed. We think of an investment that moves the value to just across the threshold. So if your threshold was 12, the investment is going to be just enough to get your value to be 12.01 at some tiny cost, at a cost of 0.001. Now, it turns out that if you performed poorly with that investment that just barely crossed the threshold, then there is an instance of the allocation problem that has equally bad performance, right? Having an investment that crosses the threshold to 12.01 is almost as though your value was 12.01 to start with. If you were going to do badly then you were going to do badly in the allocation instance where the value was 12.01 for sure. So insofar as those investments are bad, their efficiency loss is already captured by the allocative guarantee. So the investments that reduce worst case welfare further than the allocative guarantee are the investments induced by value changes that do not cross a threshold. Those, in a strategy-proof mechanism, those changes are not priced, right? In order for the mechanism to be strategy-proof, when you change your value and it doesn't cross the threshold price, your payment can't change. And so Xbone basically says that when you make investments of this type, you can't be harming other people. You can't harm other people from value changes that are not priced because they don't cross a threshold. And that's why that condition appears. Now, it turns out that the full proof actually just uses that and fits in a slide. The proof under incomplete information is longer. It does not fit on one slide, but this really gives you a sense of what's going on. Give me any investment instance. So an investment technology for a bidder, value profile for the other bidders, and a set of feasible allocations. Let's imagine the investor is not indifferent between investing and not investing. I'm going to suppress in these welfare functions, I'm going to suppress the dependence on the value profile of the other bidders and the feasible allocations, because I'm just going to hold those fixed. It will reduce clutter if I suppress them. Now, observe that if your value net of investment, if I take the value from the investment and I subtract the cost, if that leaves you worse off than if you didn't invest at all, then you won't invest at all. And so if that's the case, the investor is going to choose not to invest and not pay any investment costs, which it turns out is also efficient, right? If the investment doesn't even cover its own costs, a benevolent planner would also never undertake it. So let's suppose the only case we need to really care about is when the investment net of its cost leaves you at least as high as before. Observe that the welfare a social planner can achieve with this investment technology is exactly equal to the welfare the social planner can achieve when there's no investment opportunity, but bidder ends value is exactly equal to making the investment net of the cost. Why is that? Well, if the social planner was going to pack this bidder, she should induce the investment, in which case she gets the value V upper bar minus the cost C upper bar. If the social planner was not going to pack this bidder, then she should not make the investment and she should get a value of 0. But that's exactly as though that bidder's value was fixed at V upper bar minus C upper bar. So there are only two cases we need to consider. In the first case, bidder N is packed when his value is V upper bar minus C upper bar. In which case, well, it turns out that if this is true, it's profitable for the investor privately to choose this investment. And so what do we have? What does this say? This says beta times the welfare of the efficient, beta times the welfare of the efficient allocation and the efficient investment. I've already argued this is beta times the allocative welfare when bidder N's value is just fixed here. our algorithm is a beta approximation. So the welfare achieved by the algorithm at that value profile is at least beta times the optimal allocation at that value profile. That's how I get this inequality. But at this value profile, the bidder is being packed. And now I'm raising her value. And Exponent says this can't harm the net welfare of everybody else. So total welfare has to rise by at least the cost of the investment. But that's exactly what the welfare the algorithm is achieving, our approximation algorithm, when the bidder makes the investment. In the other case, suppose the bidder would not be packed if her value was V upper bar minus C upper bar. Then this investment is not a worthwhile investment to make. You can prove that the investor is going to choose privately not to make the investment. This is the same argument as before. This is a beta approximation just as before. What's happening here? I'm taking a bidder who's not packed, and I'm lowering her value from V upper bar minus C upper bar to V lower bar. But I'm lowering the value of an unpacked bidder, and Exponent tells me this can't hurt anybody else. So the welfare is to be the same as before. And by hypothesis, that's exactly the welfare that happens when the investor chooses not to invest. So in all cases where at least beta of this, I agree, pretty demanding benchmark that we've chosen for ourselves. Now, it turns out that subproblems can have better guarantees. So you can, instead of looking at all of the knapsack instances, I can look at all of the knapsack instances where no bidder is very big. And I can think about the guarantees in that case. An immediate corollary of our theorem is that if you look at a subproblem that has a better guarantee and its exponent, that better guarantee is going to persist under investment. And it turns out you can use this subproblem language to talk about a sense in which these exponent is almost necessary. How much can we weaken it? So this is a partial converse. It says, give me an algorithm that's a beta approximation on a problem for some non-trivial beta. These statements are equivalent, that the algorithm is weakly exponent on that problem. And second, for any subproblem and any beta prime, if the algorithm is a beta prime approximation on the subproblem, it's a beta prime approximation with investment on the subproblem. Put differently, if the algorithm fails this weak exponent condition, then I can find the subproblem on which its guarantee is strictly worse when investments are available. And this is weak exponent. It's exactly the same condition you saw earlier. The only difference is in red. Rather than worrying about all value changes, we only need to worry about value changes when the bidder is in, sorry, this is a typo. This should say N is not in. N is not packed, but is in every efficient allocation at that instance. Only in those cases do you need to worry about value decreases. Now, of course, this is a immensely impractical condition because the problems we are concerned with are ones where we can't compute efficient allocations. So checking whether this is in fact true, whether this weakening is useful, is going to be a hairy problem. But in principle, this shows you how much daylight there is. This is how much you can weaken exponent and still hope to have this kind of robustness property. Cool. Now I should wrap. There are natural extensions. We do some of them in the paper. But really the key thing here, right? The key message of the paper is that approximation algorithms, which are useful for many things, can be nearly optimal, but can get really far from optimal when investments are available. The thing that causes these are these algorithmic externalities, but you don't need to worry about all of the externalities. You only need to worry about bossy negative externalities. You can typically know if your algorithm has these just by looking at it, right? It's quite tractable to prove whether or not your algorithm is exponent. And if you can prove it's exponent, then you know its guarantee is robust in this fashion. Weak exponent is sort of sufficient. It's a converse. What would it need to be necessary and sufficient for this kind of robustness? Weak exponent is there. Some of the algorithms you would find in a approximation algorithms textbook are exponent, some are not. You know, so it seems like this is a condition that has some bite. Cool. And I should hand it over to real computer scientists to tell me what we should do differently.
Thanks. That was impressive talk for using someone else's slides. I'm quite, and probably you're also a little bit hungover, so I am quite impressed with the quality of the presentation.
Yeah, I'm impressed with timing as well.
I guess, like, you know, the sort of gut reaction of a computer scientist, I think, is like, this is a really compelling condition, and it would be awesome if there would be a sort of way to take non-exponent algorithms and smoothly, like, you know, iron them, and as an economist might say, to make them exponent. I'm wondering what you've thought about in that direction.
We have tried and failed, but it is possible we have failed because we lack the right tools or the right perspective to do it. It seems like an immensely important open question, right? It'd be nice to write sort of Hartline and Lussier, but for exponent, but we're not sure how to do it.
Another question, maybe it's very similar, is the question of, so this is kind of either you're exponent or you're not. Ideally, I would like, you know, a number between 0 and 1 that says how exponent you are, and you know what I mean, in some moral sense, and say, you know, as this number degrades, so does the guarantee.
So let me offer a version of that.
Okay.
Let's call an algorithm alpha exponent. If whenever I, you know, raise the value of a packed bidder or lower the value of an unpacked bidder, what would I need? I would need that the sort of the loss in welfare compared to, I would lose no more than alpha of the change in welfare, right? So if I raise the value by V, I need to capture at least.
So 0 exponent is exponent.
Yeah. So I'd lose no more than alpha, meaning 0 exponent is exponent. I can't lose any of the change. But you might imagine saying, look, if I raise the value of bidder 1 by 10, I'm allowed to lose 5. Right? That's a half exponent algorithm. And so you can prove a theorem that says if you have, and it's kind of straightforward. It's just plugging that different condition into the same chain of inequalities you saw. You can prove that if an algorithm is a beta approximation and alpha exponent, then it's a beta alpha approximation with investment. Yeah.
Oh, very cool. Okay, thanks.
Can I ask a completely non-computer science question here? Much more of an economics question. So here we have these problems where investments are being basically in the light of a future view to have a VCG mechanism. So in other words, I know that at some point I'm going to be involved in one of these algorithms or something that sort of approximately VCG or so on. And I'm going to make investments forecasting that, which I can see how it applies in some practical problems when, you know, now we use auctions, combinatorial auctions, and all sort of algorithms to allocate stuff. But it's limited, right? Because you can think of a problem. I mean, I'm just trying to see the real world relevance here. Is this for these kind of problems? Because in other cases, you know, I make investments in education way before I start to think what my education is going to be used for and a particular VCG mechanism and so on. You see where I'm going with this?
Yeah, so there are lots of investment decisions. You're right. No, you're right. You're right. There are lots of investment decisions where the fact that we're going to participate in a mechanism is a surprise. But there are also a lot of mechanisms with like long run participation, right? Think of like an electricity market, or if we were to run an auction for like landing slots at an airport, right? If you're United Airlines, you're going to say, okay, I'm participating in this allocation mechanism every year. Should I buy bigger planes? Well, if I buy bigger planes, that depends on whether or not I have room to land the bigger planes. And so this leads me to the obvious point that the dynamic mechanism design problem is even more complex than what
we've got here, because maybe it is good to randomly change the mechanism every once in a while if the mechanism that you're currently using disincentivizes investment. I mean, so you could fix it that way, right? Rather than trying to find the mechanism that always generates investment. You can say, well, I'm happy with bad incentive as long as they can't forecast what I'm going to do, they're still going to invest or something like that. You know, this is a very loose description.
we could hope to surprise them, or we might hope. So we don't even really understand the benchmark of what we would do with full commitment. Imagine I could say, look, I'm going to commit to a sequence, potentially randomized sequence of mechanisms that are going to be used to allocate the airline landing slots from here to infinity. Every once in a while, an investment opportunity is going to arrive for one of the airlines who got a chance to buy a bigger plane. What sequence, potentially next sequence of mechanisms should I commit to at time one if I care about welfare, right? That seems like an interesting question, and our model is abstracting from all that nice dynamic structure.
So your model would be something that you're trying to get somewhere where it's kind of at least beta good in a static sense. If you commit never to change the mechanism, the way to interpret what you've got is, in order to preserve this is beta good. If you want to interpret investments, you need this X-bone stuff. Otherwise, you can't do it. But yes, but that does leave open the possibility that non-X-bone stuff could work if you could commit to sequences and things like that.
You might imagine if enough time has passed by, if there were good investments, you've made them. So now we don't need to worry about investment anymore, or something like that.
So sorry, Shengwu, I'm going to have to drop because I have a kid situation here. Let me just ask one question. Did Scott suggest the term X-bone? I'm just trying to see if I can, guess your tastes in words.
Paul suggested the term X.
Oh, wow. Okay, so I'm updating my prior here immensely. Okay, I'm so sorry I have to drop. This was great, and I asked everything I had to ask so far. So
thank you, Yannai. I'll catch you back in Cambridge.
Thanks.
Thank you.
Great.
I don't know if we still have time for more questions, but I guess I had one. I think I've talked to you about this in Cambridge before, but like I live in an optimistic world where no investment is unproductive, and so I kind of wanted your welfare function to not take out the cost of investments. And I kind of asked you how that would change, but I'm wondering.
So let me answer a different version of that, because it's possible I misinterpreted the first time around. Mm-hmm. You might imagine saying, even though the investor privately faces this investment cost, we will not count this cost for social welfare.
Yeah.
Now, the problem there is that no guarantee will survive that, because imagine we've got there's a knapsack. You're the only bidder. You will definitely fit in the knapsack. You could pay, $1,000 to raise your value by 100. Now, if a social planner doesn't need to care about the $1,000 cost, the social planner only gets to see, oh, I get to raise Nicole's value by 100. But you will care, right? You will say, I'm out $1,000. That's bad. And then so we could sort of, my worry with that formalism is that we would need to be careful about how it played with the notion of a guarantee in order to avoid this nuking all the guarantees to zero.
Yeah, that makes sense. The other sort of kind of I haven't thought about this very deeply at all, but like another thing that I see a little bit in the CS literature is people worrying about investments that make me look good but don't actually change my value. So you see this coming up a lot in the literature on fairness and machine learning, and where there might be different groups that could invest differently in SAT prep courses and then look better to colleges without actually being a better student. And I'm wondering if this kind of, what if investments are fake or something? What happens in your formalisms?
So I guess I need to think carefully about that, because my most, my naive way of modeling that would make on my naive model, my fake investment would look a lot like misreporting my value. And bidders already don't want to do that because it's a strategy-proof mechanism. And so we would need to think of a formalism that somehow put daylight between a misreport of a value and a fake investment. And that seems like that would take a conceptual insight that, you know, I don't have at this minute.
Yeah, okay. Yeah, I haven't thought this through at all. It just came into my mind.
Anja, do we?
Yes, yeah, it's more a curiosity than really a question. Okay, so I mean, I have seen this idea of non-bossiness in several environments. Okay, and it always kind of seems like a natural constraint, but you never come up with a a proper explanation of why you don't want mechanisms that are non-bossiness. I mean, certainly, I mean, your definition of non-bossiness is particular because it only means with respect to the allocation, you're leaving aside money. Okay, so in that respect, it's quite different to the standard definition of non-bossiness. But still, I was wondering whether this idea that the non-bossiness arises as a natural concept when you allow for investment is new or has been exploited before.
So I think the connection here between non-bossiness and investment is in some sense new, but it, I think, draws on a chain of informal argument people have offered for some time, right? People have often said, the reason you want your mechanism to be non-bossy is because the game is bigger than you think, right? That even though we've written it down that each bidder only cares about their values, there is some hidden reason they want to alter or damage the other players. And if you had a bossy mechanism, you would create opportunities, unmodeled opportunities to interfere with the other players that they might undertake, right? And so this is kind of an explanation in that line. It's like non-bossiness is about robustness to strategic opportunities that we modeled only imperfectly when we went down to this view of like, of mechanism design.
I see. Thank you. Yeah, I mean.
Can I ask a stupid question? Is it obvious that the bossy externalities are negative always, or I mean,
No, you could have bossy positive externalities, and those would be great. You could imagine that you invest to raise your value, and then that helps the algorithm even more. It discovers a better allocation than before, and those would be great. It turns out those are not a danger to the welfare guarantee. So it's very specific when we say when we raise the value of a packed bidder, we shouldn't hurt anybody else. You might imagine saying, what if we lowered the value of a packed bidder without going past the threshold? Should that not hurt anybody else? It turns out that doesn't matter.
But in a knapsack kind of problem like you have, because I'm trying to think what. So, wouldn't they arise in situations where instead of having I can't conceive of one. Because here you have like a capacity constraint, right? In some sense, that's what a knapsack is. So my natural instinct is that they would naturally arise when you have the opposite of a capacity constraint. Although I don't understand what the opposite of. So I'm trying to figure out what an example would be, basically.
So let me give you an example, even with the knapsack, right? Here's an example of a bossy positive externality. Remember the smart greedy algorithm? It runs greedy, it compares that to the best individual bidder, and it picks whichever is better. It turns out that there can be instant cases where we run the greedy and you're the best individual bidder. So we pack you instead of the greedy set. And if we raise your value high enough, you will get packed in both the greedy phase and in the best individual phase. And so we'll pick the greedy packing and pack a whole bunch of new people we didn't think to pack before. And so that's a bossy positive externality. You've improved the allocation by raising your value.
Okay.
Okay, do we have any other questions?
I mean, it's just a wild thought that crossed my mind, but a positive bossy externality by playing with the cost, can you convert it into a negative bossy externality always? I mean, it's just a wild thought. I mean, I haven't got to the details.
I mean, I think there may be some connection, but it's super not obvious to me how to make that connection. In our model, right, we are taking the worst case over all investment costs, right? So we are, we can we have to consider there's a given investment change and we can make that expensive or inexpensive. And we have to consider the worst case over all those scenarios. So in that sense, it's not, it can't be that just changing the cost flips the sign.
Yeah. Okay. So let me put it differently. Do you have an example of a mechanism that is X-bound, but that still allows for positive boxy externalities?
Yes, it's the threshold auction that corresponds to the smart greedy algorithm in the knapsack. That has bossy positive externalities. So it's a bossy mechanism and it's an X-bound mechanism.
Thank you.
Should we stop the recording?